Swayam Prabha. Digital India. Educated India.
Welcome. We are in the class of high performance computing for scientists and engineers. This is the first module, fundamentals of parallel computing, on which discussions are going on, and we are continuing with the lecture on architecture for parallel computing. Well, this course, as it is titled high performance computing for scientists and engineers, is meant for a wide class of audience with backgrounds from different fields, which is not only strictly computer science, but also students from physics, chemistry, mathematics, biological science, different fields of engineering and different other science application domains are probably participating in this course. Therefore, we can very well assume that all the students do not have background in computer science, especially in computer architecture. So, while discussing computer architecture in these few classes, I will try to give some fundamental ideas on parallel computer architecture. Again, keeping the fact in mind that many of the students do not have this background and the concepts are very new to them, will repeat some of these concepts later in this class. Maybe in the next class we will see some of the concepts, at least some pointers to the concepts which are discussed in today's class will be touched upon, and later also when we will do HPC programming, we will some time get back to these concepts again. Again, for the wider audience, especially who are not from computer science background, we are discussing the concepts on parallel computing architecture because when one will try to implement HPC for their own scientific or engineering purpose, or when somebody will try to apply some of the high performance computing techniques, well developed techniques commercially available, or community developed softwares which use high performance computing resources, when they will try to apply these software, they will try to use this software, sometime they need to have some idea on the architecture on which they are working. That is the key to get best performance using high performance computing. So, you need to discuss the concepts, and as I said, we have already discussed few of the concepts here, like we started from architecture of a sequential computer. We discussed about interconnect networks, how different processors can be connected via bus, or how different processors and their memories can be connected via interconnect network switch. We have discussed about processor arrays, multiprocessors and multi-computers, and one might note down that the processor arrays and multiprocessors, they give a shared memory platform for high performance computing or parallel computing, and multi-computers give distributed memory platforms. In the subsequent class, we will discuss in detail about shared memory and distributed memory. Then we have some discussion on how HPC clusters look like from the architecture point of view and how are GPUs or graphics processing units. Then we discussed about communication costs, because when multiple computers are working together, there is a need to communicate in between them in terms of exchanging information or data. And apart from the computer's processing cycles, apart from the number crunching that the computer is doing, how much time is allotted for the communication across processors. We have also looked into that. So, today we will be looking into classification of parallel architecture, and we will see something named Flynn's taxonomy. As we have discussed in one of the previous lectures also, that computer architecture is an evolving area. What we see today as GPU was not there 20 years back, and what was the fastest supercomputer in 20 years back, probably if we consider its performance, it will probably not be among top 5,000 supercomputers today. So, computer architecture is an evolving area in many aspects. However, Flynn's taxonomy is something which classified the parallel computing architecture, and even today any of the high performance computing platform can be classified in one of the classifications given by Professor Flynn, and that is why it is important to look into Flynn's taxonomy too. So, one important concept is parallel random access machine or PRAM. See, there are more than one processors, P number of processors, P is greater than 1, connected to a same unbound memory space. It is a huge memory space in which many computers are connected, and all the processors can access the memory space uniformly. So, it is a large UMA memory space, it is the same memory space, all the computers are connected, and many processors are there, a large number of processors are there, they are connected to the same memory space and they have the same address space. So, any variable A for one processor is seen by all other variables, the same variable which is shared by all the processors. So, we call it to be ideal shared memory machine, it is a shared memory machine, and where the memory has no bound, it is a large memory, there is no restriction regarding memory, and any number of processor number greater than 1 can be considered for this. And this machine, parallel random access machine, can be classified as following. One can be exclusive read, exclusive write PRAM, that one, when processor is reading or writing a particular location of the memory space, other cannot do that on the same location. So, it is a same address space which is being shared by a number of processors, but if one processor reads one of the memory location, one of the locations in the address space, the other, or writing anything, writing in any of the locations of the address space, that location the other computers cannot access. So, if somebody is reading, some computer is reading a memory or writing a memory, other computers cannot do that, and therefore, there has to be some sequentiality. If one computer is doing that, others have to wait. Parallelly, a large number of processors cannot, or parallelly more than one processors cannot go to the a particular memory location. The next is exclusive read and concurrent write. When one processor is reading a particular location, others cannot read the location, but when one is writing to that locations, other processors can write concurrently. So, at the same instance, many processors can write the same memory location. Concurrent read, exclusive write, which is the reverse case of this, that one processor is reading a particular location, then other processors also can read that location, but multiple processors cannot write in the same location concurrently. Writing in the same location concurrently has an issue, that if all the processors try to change the variable at the same address space, there can be certain conflict or contention, which we will see in the next slide. And the fourth one is called concurrent read or concurrent write. All read write in the memory location can be done concurrently by multiple processors. That means, if one processor accesses to one memory location and reads or write there, the other processors can do some operation on the same involving the same memory location. There will not be no wait time, there will not be any wait time for any of the processors, because some other processor is working on the same memory location, and therefore, all the processors can parallelly operate on the same memory location, and this will be the ideal architecture for parallel machines. Now, let us see what are the issues if we can think of a concurrent read, concurrent write model. concurrent reads do not create semantic discrepancies, because it is the same memory location, everybody is reading, nobody is going to change anything there. There can be some contention, because due to bandwidth etc., all the processors are trying to jump into the same memory location. Like you have a newspaper and you are going in a public train, you have a newspaper, you are reading that, and two people from your right and two people from your left wants to see the headlines of the newspaper. So there can be little contention, however everybody can read the same newspaper. But concurrent write, you have a piece of paper and you are writing something and four people from both your left and right are jumping together to write at the same location, that is difficult. Concurrent write means the same data is concurrently changed by several processors. So one processor is trying to write a is equal to 1, the other jumps on there and tries to write a is equal to 2, the next one jumps there in and tries to write a is equal to 3. There might be contention among the processors if they are writing a large memory, if they are writing lot of data in a particular space and writing together, there might be contention, there might be conflicts also. Therefore, some of the special protocols are followed if we try to access concurrent write. If we try to say that processors can concurrently write on the same location, we have to use some protocols. And what are they? Arbitrarily any of the processors are allowed to write in the memory space, other cannot write that. So though we say it is a concurrent writing access given to all the processors, but when say more than one processors are trying to write in the same memory location, to avoid any contention, will allow one to write there. Once his writing is finished, the next one will be allowed to write there. Though it is a concurrent write, but there will be some sequentiality in the write, and will write, will not write, that will be decided arbitrarily. Common, if the concurrent data is identical, all may be allowed to write it. If everybody is writing a is equal to 2, everybody can write that. Then no other processor has to wait for writing it, and these protocols are followed so that there is no conflict among writing the same in the same location. Priority, there is a priority among the processors. Say processor number 5 is given priority. So if it has to write a is equal to, it will write it, others cannot do. Once its writing is finished, the next processor in the priority list will be allowed to write it, the rest will be barred. And the fourth one is important, which is very important in many of the scientific computations, that in many cases the processors work in parallel, find out some value, and finally you need a sum of the values obtained by the processors. Say you have to compute for an infinite series. Of course, you cannot compute for infinite terms in the series, but you think to compute first 1 million terms of that series. And an infinite series is basically sum of first 1 million terms in the series. It is near infinite series, I will say. So you have 1000 processor, each processor is summing up 1000 terms, and after the calculations are done, all the sums coming from these 1000 processors will come together and you will write the final sum. So when the final sum is coming, everybody is adding, in order to get the final sum, everybody is adding to the memory location. So there will not be any conflict, they can concurrently add up to their values to the memory location, and a concurrent write can be allowed. And this is used in many cases. But this is for shared memory machine, that even if the processors are working in parallel, in order to access the memory in terms of read and write, some of the models are usually followed. But for distributed memory machines, they are not writing to the same memory location. All the processors have different memory unit and they are writing at different memory locations. Therefore, these issues are not there. However, they are writing to a common file system. When all they are connected to a common file system, and when they are writing their results, they are writing to the common file system. And again, if concurrent writes are allowed, certain protocols are followed such that the files are appended, etc., so that no data is overwritten. Well, now we come to a much broader classification of architecture of parallel computers, and this was given by Professor Michael Flynn in 1966, which is based on the number of concurrent instructions and data streams that the parallel computer is followed, and this is called Flynn's taxonomy. This is 1966. Today in 2021, the Flynn's taxonomy is very much valid and quite well utilized when we discuss about parallel programs. The first one is single instruction single data stream or SISD. The next one is single instruction multiple data streams SIMD. The third one is multiple instruction multiple data single data streams MISD, and the fourth one is multiple instruction multiple data stream. So, any of the program, any of the parallel programs must follow one of this architecture and should be written accordingly. So, first is single instruction single data stream or SISD, and this is very much like a sequential computer. Computer in this category can decode a single instruction in unit time. So, there is a processing unit, there is a data pool, there is some instruction given to it. Once a instruction comes, the processing unit takes data from the data pool and processes that information. So, it is exactly how a sequential computer should work, or how a single computer should work. It is a non-parallel computing method, that there is one data pool, CPU is taking data from the RAM, one particular location data, one CPU is accessing one data and it is getting one instruction, so it is processing it. An analogy is given, classical analogy is given as check-in desk in the airport. You go to the check-in desk, you present your ticket, the person sitting at the check-in desk looks into the data pool, sees what is your ticketing number, PNR, what should be the seat number, prints boarding pass and gives you. And the next person comes, he has to wait behind you. Once you are done, the person takes the next person, takes the ticket, looks into the data, prints the boarding pass and checks in him. It's a SISD means a single desk in the single check-in desk in the airport counter. And this is the way an ordinary computer or a sequential computer works. The next one is single instruction multiple data stream, that there is an array of processors. It is like a vector processor or an processor array which is executing same instruction but on different data. So, a single instruction is given to all the processors. Let they are asked to add two numbers, but each processor is getting two different numbers and adding them. In a classical example is, many desks are there in a airport check-in counter, and a supervisor in megaphone giving instruction that you take everybody's ticket, look into their check-in data. There is a 4 counters in parallel. So, at a go 4 person can stand in 4 counters, give their tickets, he will check their data. Then the supervisor is giving instruction that print their boarding pass. So, 4 boarding passes will be printed and 4 people will be done. So, instead of processing 1 at a time, 4 at a time can be processed. And this is also very extremely heavily used, especially in scientific computing aspect. We can think of IT industry jobs that credit card information is being processed for 1 lakh people in 1000 computers. So, each computer is looking into 1000 people and doing the same information, same work, that in last month how much they have spent and how much they have put into their credit card. So, what should be their balance. So, instead of one computer processing 1 lakh, which would have been the SISD architecture, this is working in SIMD architecture. That same operation is being processed by all the computers, however, on different data. For matrix vector multiplication, we will see some of the examples in next class. Say we ask a parallel computer that you have to do a matrix vector multiplication, and each computer will take care of one of the rows of the matrix. So, it is 1 row per computer. So, the entire matrix can be computed at a go, because each row, instead of looking into running a loop over all the rows, each computer is responsible for 1 row, and many computers are doing same work, that taking the first element of the row, multiplying with the first element of the vector, adding with the second element multiplied with the second element of the vector, and so on. So, finishing for each row. So, this is used in many shared memory and GPU based applications, the shared single instruction multiple data stream calculations. The next one is multiple instruction single data stream, which is called MISD. Some people also consider this category to be empty. That means that this is not very much used in parallel computing, that you have a same data pool, but there are multiple instructions which are operated over the same data stream. So, we can think of something like that, for a same passenger different desks are doing different job. Like once a processor goes one desk, he gives his ticket, so the PNR number and all the information are obtained, and one desk is processing his ticket, other desk is checking his luggage, other desk is printing his ticket, etc. So, instead of one person working on the same data and doing different operations, different persons are doing on the same data, different persons are doing different operations. You can think of income tax department work, another analogy, that a PAN is given and different financial information is required, how much tax he has paid, what are his bank transactions, what is his foreign money exchange, etc. So, it is the same data, it is the same PAN against which all this different information can be found out and differently processing this data. So, if one needs to operate, especially for scientific computing, for post processing aspects, when one needs to get several parameters out of the same data set. Say you know a vector field and you need to find out the convective acceleration, you need to find out the vorticity, you need to find out some skewness in the velocity vectors, etc. So, on the same data field, you ask the computers to, one of the computers to read the data field, and the data resides in the same shared address space, and different computers in parallel is looking into the same data in a concurrent read mode and processing different information on the same data. Well, the next one is the most parallelized version, multiple instruction multiple data stream, or MIMD. There are many CPUs, each CPU can access different memory, each CPU can work on different memory location, and each of them are in parallel running their own data. So, there is a data pool which is accessed by different computers. It can be NUMA, it can be multi computers with different data, because it is a multiple data stream, and there are number of processors which are processing different operation. It is not the same instructions pool, it is different instruction pool which is operated by different computers in parallel. However, these computers are some way, we can see these computers are some way connected to each other. There is some connection in between the computers, and they can exchange information, they can pass some message from one to other, they can have some synchronization. So, many desks working at their own pace with different data synchronized, but they have a central database. So, there is some synchronization in between them, both in terms of data as well in terms of the operations. It needs communication between, more communication between each processors, because they have much flexibility. In order to have synchronization, they need to communicate more. When ants are moving in a line, it is only communication with the previous or the following ant through some chemical exchange. It is less amount of communication is required, but when you give more flexibility, that say 15 students from 15 different backgrounds are coming to a examination hall, and after the exam is over, they will go out and catch their buses. However, they will reach the same destination. They need more communication if they at all need to do that within the stipulated time. So, more flexibility means if you need to have synchronization, if you need to use same data, you need more communication. All that is that more flexibility means more communication, and this is heavily used in scientific computing. Many of the scientific computer problems will use MIMD because it's more flexible. You have a much complex algorithm, you need much more flexibility to parallelize it and get the efficient parallel performance. Most of the top 500 supercomputers follow this architecture. They provide a platform where you can run programs which are following MIMD architecture. So, we will look into programming models in MIMD, because MIMD are the is one of the very important architecture or paradigm for high performance scientific computing. The first one is single program multiple data, that the same program runs in the system. It is the same executable file which runs in the system, and the executable file, as same executable file goes to different processors, it works there. However, different instances of the program through if-else statements runs in different processors and operates on different data. It is a same program which has different instances, and depending on the processor number, depending on the part of the data that processor is connected to, this is operating. So, when you write a scientific program, or say we talked about matrix multiplication, matrix solutions, etc., and ask many computers to work in parallel. We do not write different programs for different computers. We write one program which is executable over different computers, but let us think of a matrix which has a varying bandwidth. The number of non-zero numbers in each row is different. So, when it goes to a computer when it goes to a part of the matrix where there are, say, 80 non-zero numbers, a loop over 80 runs for that particular rows, 80 elements. When it goes to another row where there are 13 non-zero numbers, we run a loop over 13. So, how do you do it? We have some idea of about the matrix. So, in the program we write, if it is in these rows, the computer which is getting the processor for these rows, it will operate for a loop 1 to 80. The next computer which is getting the rows where there are only 13 non-zero numbers will run a loop 1 to 13. So, that way, using if-else statements, we can run different instances of the program and different computer, and it actually runs as a multiple instruction, multiple data model. However, it is a single program, it is not different executable. Again, you use some of the commercial software, say LAMD or GROMACS or ANSYS Fluent, you run in multiple computers, is the same executable which runs in different computers. Each of the computer, if you go to if you say do a top or see what are the programs being run in different computers, you will see the same program is running in each of the computers. This is used in almost all scientific and engineering applications with distributed memory over large number of processors, that you do not write many programs, you write a same program, use some if-else statement to provide different instances which will run at different computer. The next one is multiple program, multiple data, that means different executables are now running at different computers, and more than one independent programs are running concurrently, and this is used in gaming, playstations, more on entertainment industry, more on visualization industry, but scientific and industrial engineering applications, scientific and engineering applications mostly rely on single program multiple data model. So, these are the few textbooks which we have followed over this class, the Grama Gupta Karipis Kumar parallel computing book, Quinn's MPI and OpenMP parallel programming book, NVIDIA's CUDA C programming guide, and some of the notes and pages from Wikipedia. If you Wikipedia has a very good repository of these discussions. If you need to find out some of the details of some of the concepts with nice animations, you can search, do a Google search, go to the Wikipedia page, look into their text and narration, and most importantly, you can look into the references given by the Wikipedia and go to the reference papers. There are very good, some of the very good papers in parallel computing which is referenced by Wikipedia. And in the discussion on parallel computing architecture, our conclusions are, we have discussed an architecture of several parallel computing infrastructure and also looked into the processor memory cache functioning. We will again look into processor memory cache functioning when we will discuss about shared memory platforms in more detail. As I said that we need to, some of the concepts will overlearn it. We will discuss these concepts number of times. We looked into interconnect networks and the performances, including the cost of communication. We have seen how HPC clusters and GPU cards functions, at least some introduction is given to that, and Flynn's taxonomy for parallel computing and the programming models, single program multiple data and multiple program multiple data, and different PDAM access models are also shown. Well, thank you.